Dr Richard Parsons, thank you very much for joining us here on AU Manufacturing Conversations.
Yeah, my pleasure to be here.
A stock opening question, as it always is how did you get here and what do you make?
Yeah, so as you said, my name is Dr Richard Parsons. I'm the founder and CEO of Kite Magnetics. Kite Magnetics is a relatively new venture-backed aerospace manufacturing company located right here in Melbourne. We make very high-performance electric motors, specifically for electric aircraft of all sizes. So our electric motors use a new type of magnetic material called aeroperm. Aeroperm was developed by Professor Kiyoshi Suzuki and myself at Monash University, where I worked for the last 10 years. And what's unique about our electric motors is that by using aeroperm, they're much smaller, lighter, and more efficient than our competitors. And that all translates to more flight time and more payload capacity for our customers. Right now, we're just getting up and running. We've only recently spun out of Monash in the last 6 months, having raised just under $2 million. That allows us to now have a team of just under 10 engineers working hard to build out our first product, an electric motor for training aircraft, and a world-class electric motor test facility right here in Kite, Victoria.
Right.
So that's in a nutshell.
Well, that's a good, solid, brief explanation. We'll probably get into some more detail as we go along, so fill in any remaining questions about how you got here. Tell me about being from a family of engineers, and if it was always a question of, okay, Richard, you can be any kind of engineer you want to be. I'm interested in coming from a family of engineers and your decision to pursue that career path.
For anyone who knows me, I'm definitely an engineer through and through. I'm someone whose all my interests, hobbies and obsessions are very much engineering focused. This wasn't necessarily a foregone conclusion growing up, although I did come from a big family of engineers. My father and my grandfather and my uncles and cousins and my brother, all engineers of various backgrounds. And so for us, we're definitely heavily encouraged to pull things apart at the kitchen table. And that was a regular occurrence. So although I've been an academic for many years, I'm perhaps a little bit unusual in that I'm also someone who built a big CNC milling centre in my garage, robotic arms and 3D printers, and learned to code and do a bit of machining and all the rest. Becoming a materials engineer was a little bit of a wandering path. So my background is actually materials science. So I did a science degree back in 2007. And the reason for going down the engineering path and the materials path was that I could see, science, I love the physics, I love the mathematics and the chemistry and the fundamentals, but I also wanted to work on something where I could have a more of a hands-on, perhaps more application-driven impact. And that's where materials science and engineering is perfectly suited. Getting involved in what I worked on for the last 10 years as a magnetic materials researcher, that came about all the way back in 2007, where I was studying science and I took some units in atmospheric science, and it was abundantly clear to all the professors, even back then, that unfortunately a very large part of our future is going to be driven by the impacts of climate change. And so I wanted to work in an area and sort of drive my career in an area where I could have a positive impact in that space. For me, that meant working either potentially on battery technologies, incredibly important today, very relevant, or alternatively, where all that precious energy in the batteries is ultimately consumed, and 50% of the energy produced on the grid is consumed in electric motors. My mind was made up for me when I met Professor Kiyoshi Suzuki, who was one of my undergraduate professors all the way back in 2012, I think it was, and got really interested in what he was working on. So he's someone who's incredibly knowledgeable about magnetism and magnetic materials, and was working in this unique field of advanced magnetic materials for very high-performance electric motors. So after speaking with him and touring his lab, like many postgraduate students do, I ended up going down a path of starting a PhD and then a postdoc, and then becoming a researcher and a lecturer, and finally the head of a research platform before stepping away to start Kite Magnetics. So yeah, a long journey to become a materials engineer, but that's it.
Right. I'd like to know a little bit more, please, about the nanocrystalline materials that you've been researching. You mentioned aeroperm, which your PhD supervisor discovered. Tell me a bit about the nanocrystalline materials you're researching in your PhD and in further work, and about your 2018 breakthrough with them.
Yeah, sure. So aeroperm physically looks a little bit like kitchen foil. It's a thin, shiny, metallic foil, about 20 microns in thickness. It's used in electrical devices to guide and control magnetic fields. So it can be used in transformers and inductors and filtering components, and of course, electric motors and electric generators. Aeroperm itself is what's known as a nanocrystalline magnetically soft core material. The way it's made is really interesting. A bit like cooking. You start off with a handful of iron and a pinch of boron, a sprinkle of silicon and other elements, and you put them all into a crucible and you melt them down into a liquid. You then take that liquid and in a process known as planar flow casting, you eject that liquid through a very small orifice, through a nozzle, out onto the surface of a spinning copper wheel about the size of a dinner plate. The surface of that wheel is moving at about 100 and something kilometers per hour. And as the liquid metal touches that, it's cooled at over 1 million degrees per second. Really, really, really quickly cooled down to a lower temperature. What this means is that the liquid transitions to a solid, and it does so without the atoms having enough time to sort of rearrange and find their natural ordered structure that they'll prefer to be in. And so you end up with what's called a metallic glass or an amorphous metal, which itself has some really unique mechanical and magnetic properties. But we take it a step further. We use our own proprietary composition and our in-house proprietary processing technique, where we take that foil that's been produced in that one step, that planar flow casting, and we heat it back up very rapidly into a specific temperature for a specific time and then cool it again. And through doing this, you form very, very small, so we're talking tens of nanometer size crystals within this amorphous metal. And these crystals embedded in this amorphous matrix is what gives this fantastic magnetic properties of this material. Specifically, by doing this, you end up with 10 times smaller energy loss than the magnetic materials you use in electric motors today, which is really, really important because around half of the energy lost in a motor, a well-designed motor, will be in these core materials. So we can significantly improve the efficiency. Also, very importantly, we reduce the amount of waste heat produced by motors, which as they're thermally constrained devices, really dictates how much power you can pull out of them. So the lighter they are, the cooler they are, the more efficient they are when using aeroperm.
Right. It sounds like your cooking recipe has a lot of smarts tied up to it. I imagine it's quite hard to copy unless you know exactly what you're doing. Is that the case?
Definitely. It's all in the head of the head chef, knowing the secret process, the secret ingredients and a bit of know-how. And that all came about through a lot of hard work, of course, by many researchers before us, standing on the shoulders of giants and all that. But our contribution came about in around 2017, 2018, when we developed this new alloy and new process that allowed us to make aeroperm. And to give a bit of a history there of the commercialization process, which I think could be especially interesting for your listenership, we first developed this alloy. We knew the properties were fantastic, and we've been working away at it, especially Professor Suzuki for his entire career. Essentially, this is almost his life's work in many ways, to improve these properties of these materials over decades, to the point where in 2018, after a few significant step forwards, we're right at the point where it's like, okay, these materials are ready for prime time. They're ready to get out of the lab and go into industry and be used. And so we went out and we spoke with people in industry, and they said the same thing. These properties are amazing. It's fantastic. To use an analogy, it's a bit like we've gone back in time to the 1940s with the role of the latest generation carbon fiber to aircraft manufacturers who are building things out of aluminium. They loved the properties, but they didn't have any of the tooling or the know-how, the experience of how to process that material, where to use it, how to optimize the parts for it, how to scale up production. And so we had all these questions from industry about, well, how do we make more of this and how do we optimize, in this case, motors to use them? And so we went, okay, yes, and went back to the lab. And after obtaining some more grant funding and spent another year, we showed that we could actually scale this material production quite easily, going from literally grams per day in the beginning to then, well, in the very near future, hundreds of kilograms per hour of production. And so industry, very happy. That's great. They also had questions, well, how does this get turned into an electric motor? How do you take this steamed kitchen foil, process it to turn it into the core that can be used in a motor? And so again, more grant funding, more years in the lab, and we produced a proof of concept electric motor, went through all the processing steps and showed right off the bat, even with some pretty crude processing techniques, that yes, we can improve the efficiency of a small motor by 10% just with a direct replacement, no optimization. And so again, industry, very interested, very excited, but at the same time, they said, this is great. If you can just now, license the technology to us for a little bit of money, we promise we'll go away, we'll do something with this in the near future. It could be 5 years, it could be 10 years, we'll do something with it. By the way, if you could just tell us all the things you've learned over the preceding years, all that know-how, that'd be great, wonderful, thank you. And to me, that I wasn't especially comfortable with that. I really wanted to see this technology that we'd worked so hard to get ready, moving a bit quicker and definitely guaranteeing that it would have a direct impact, not just in 20 years, but even in 5 years. And so that's when we really started down the process of thinking about, well, what if we took the reins here and we spun out a company and did this, at least the parts we can ourselves? And that's the sort of the beginning of the Kite Magnetics journey.
And that was what prompted you to take a leap into the great unknown and just say, oh, I'm going to quit my researcher job and to put it all on the line and start a company.
Something like that, yeah. It was definitely more of a slow, gradual transition than just a one-day an epiphany and then I put in my notice. So that process of figuring out how do we start a company, that was all very new to me, although I'm probably someone who's maybe always had a bit of an entrepreneurial interest. I hadn't done that before. And so we went and spoke with the tech transfer office, whose job it is at all universities to get the tech out of the lab and into industry. And they put us in touch with a couple of venture capitalists who very politely sat and listened to my lecture essentially on the material, all the wonderful equations and figures. And unsurprisingly, that didn't really go too far. So at that point, I decided, well, look, I really need to have a better understanding of what it means to be a very successful entrepreneur. And so thankfully, us academics are very good at doing research. And so I read all the books and listened to all the podcasts and watched all the videos and probably just as importantly, went out and spoke to as many other entrepreneurs as I could find. People, ex-academics who've pulled technologies out of their labs, who've raised millions, in some cases tens or even hundreds of millions of dollars at this point, and asked them over and over, how did you find the process? What was the road bumps you ran into? What would you do differently? And who are your investors? And who are your first customers? And how did you recruit? And 100 other questions as well. And started to build a bit of a picture of what that process would look like. And then in parallel, I was very fortunate to get involved in a couple of amazing programs here. At the time, it was the on-prime program by the CSIRO, which really encouraged us to get out of the lab and go speak to people who are potentially customers for our products. And that, of course, that's a very useful step and a required step for any startup, but not one that, at least for myself as an engineer and someone who'd probably be more comfortable behind the desk in the lab than out on the street, talking to people, took a while to get used to. But yeah, through many hundreds of conversations later, we managed to work through all the possible use cases for our technology, of which there are many, and isolate those that are most likely to lead to a successful product.
What problem does it solve is an obvious one, but unless you actually go out there and talk to people and find out what their problems are, you're probably going to be asking the wrong sort of question about that.
Exactly. Any investor who works with early stage, deep tech, university technology spin-outs will tell you the same thing. Every academic comes to them first and foremost and says, I've got 1,001 applications for this. It's a brilliant magic material. And they say, that's fantastic, but we only need one. We just need one customer, one application that they're willing to pay for that technology. And so for us, we originally thought, we worked with the automotive industry for many years. They partly funded some of our research. And so we knew that they would not be a good fit, despite what you may think. That was because in the automotive industry, they're incredibly cost sensitive. You think about producing tens of millions of vehicles or motors per year. And so then for them to drop in a new material, it's actually quite a challenge. For us, brand new processing, brand new materials technology, it's always going to be a low volume production in the beginning, figure out those processes. And so we looked at, what are the high value applications? Who has a huge need for lighter, more efficient electric motors? And that's what we thought, maybe the drone industry. Drones, they can fly for 20 or 30 minutes. In some cases, they're carrying a $100,000 camera payload or a LiDAR payload, or maybe they're used for spraying crops or distributing fertilizer and 100 other things. And so we spoke to hundreds of people in that space, and we learned that, yes, huge demand for more flight time. However, terrible business model. They're buying motors that cost tens, hundreds, maybe a few $1,000s at most. And they're practically a throwaway commodity coming out of Asia, these electric motors used on drones. And so it's a very difficult market to work in, even with a new, better technology. And so that's when we started focusing on commercial aviation, so electric aircraft that you can fly in. And that's where we found this perfect sweet spot of incredible need. You've got aircraft manufacturers out there, literally engineers on the shop floor with pen knives, scraping off grams of material to get seconds more flight time in the case of defense capabilities, who are also in a position where they're used to paying tens, if not hundreds of thousands of dollars for power plants and aircraft. And so that's where we can enter that market and compete quite successfully. And so that's where we are today.
So it was the novelty of it. It's an emerging market. It's not commoditized, and it's demanding very high performance. And I imagine some other factors too, but those are some of the important ones.
For us, it was also a case of where we think we can have a big impact, again, on the climate-focused side of things. If you think about electric vehicles today, they're not exactly sold, but they're definitely heading in that direction. If you can buy a car that can drive you 800 Ks on a single charge, there's not many people who want to drive 8 hours straight or more. But when you think about electric aircraft, you're in the air sort of 30, maybe 40 minutes. And then with your reserve requirements, you've pretty much got to land. It's very limiting right now with today's batteries. And so what we're hoping is with our technology, we can help accelerate that adoption of electric aircraft by enabling them to fly a lot further sooner, which is, for me personally, very important. I mean, if you think about the impact that aviation has on the climate right now, the global warming impact, the climate change impact of aviation is about 3 times that of all Australia's emissions. It's more than all of rail and global shipping combined. And it's a very, extremely hard industry to decarbonise, unfortunately. And so if we don't start working on that technology today, then it's going to be too late if we want to hit those 2050 net zero milestones that all the airliners are committed to.
What you're going to be selling to begin with. I think last time we spoke, you mentioned it would be retrofit kits for training aircraft. Tell me about that and what you're going to be selling further on down the line.
Yeah, exactly. So we're manufacturing, of course, the material and the motor itself, and also packaging that with an off-the-shelf inverter solution to make what we call an electric propulsion solution for small training aircraft. So many people don't realise that you can buy an electric aircraft right now. There's companies selling them around the world. There's another flying at flight schools here in Australia. As mentioned, though, they're really limited on that flight time. So we're developing a lighter, more efficient electric motor solution for those aircraft that will enable them to be in the air that bit longer so that they can get through more students in a day or more skydivers or tourists or whatever it may be that they're doing. So the first product that we're making is suitable for small 2-seater all-electric training aircraft. That will be an electric motor, inverter, propeller, potentially propeller governor as well, and the integration into the aircraft for that. So you think what's in the cockpit that the pilot interacts with.
Tell me about your goals for 23, what you're going to be developing, releasing, showing to the public and to customers.
So next year, not far away, in 2023, Kite Magnetics will be showing up our first product. So we're going to be at Avalon displaying our first full-size electric motor, which will be our KM100. That is a 100 kilowatt peak, 75 kilowatt continuous electric motor suitable for 2-seater training aircraft. Over that year, our major milestones will be in the form of actually getting that integrated into some of our partners' aircrafts, and actually, potentially getting them on the runway and doing some high-speed taxiing and working towards those first test flights. We're really keen to move as quickly as we can. Got a lot of catching up to do as a small, early-stage organisation to some of our competitors. And so we want to start getting as many hours of not just internal test data in our test facility, but actual flight time under our belt, because you really don't learn all the unique challenges in the aviation industry, of which there are many. You don't get too many electric cars getting struck by lightning or struck by birds at 200 k an hour, or having to deal with icing of the intakes and all the rest. And you only learn about those things once you're out there on the airfield with real hardware doing real flights. That's kind of our North Star right now, is getting our motors into the air as quickly as possible.
If you can see into the future, when do you think we'll be flying from Sydney to Melbourne in a plane using your propulsion system, or is that perhaps too far in the future to cast your gaze?
No, look, that's definitely the goal for us. In fact, one of the things we try and communicate with the team is that if everything goes well as a company, we're in this very unique once-in-a-generation position right now where the motors we're developing today and the technology we're developing today could be the next technology you see on the aircraft in the decades to come, just like in the 50s and 40s and 30s. We saw the fledgling Rolls-Royce, the GE, the Pratt & Whitneys of the world getting established. And so once you get to that position as well, you've got this huge moat of technology around you that it's almost impossible for a new gas turbine company to get started today. And that could be us in the future, in a decade's time. So in terms of getting an aircraft from Melbourne to Sydney, definitely that's not going to be anytime soon. I've spent the last 9 months speaking to as many people in the aviation industry as I can, trying to form a good picture and a strong conviction around exactly what's possible with today's technology. Talking to airliners and maintenance technicians and pilots and regulators and everyone in between. And the consensus seems to be that right now today, if we talk about what we can do at the moment, that is, your small two-seat training aircraft right now. And in the next sort of 2 years, we'll be seeing more short-range conventional takeoff and landing, mostly retrofitted aircraft coming online. So these will be aircraft that take off from, your regional airfield, and you might go up and do a bit of a short tourism flight, or it could be a private pilot, using an electric aircraft, which is cheaper to maintain. It could be people doing skydiving or short delivery runs for packages, ecotourism, island hopping, all these applications where a short flight time is not a limitation. By the end of the decade, I think we'll be starting to see the first high-powered, lightweight, fuel cell-powered aircraft coming online. So these are all electric, where you've got hydrogen on board, not for combustion, but for generating electricity, which is used to help propel the aircraft forward using electric motors as the propulsors. And that's really what's going to be required for these longer flights. If you want to go Melbourne to Canberra, yes, you can probably do that on a 9 to 19-seat aircraft by the end of the decade, if all goes well. But Sydney to Canberra versus Sydney to Melbourne, that's going to be a much longer timeline, I think. That'll be, looking towards next decade and beyond.
Obviously, there's a lot of interest in electrifying as much as possible. Saul Griffith's very good book got a little bit of attention early in the year, and we're currently looking at gas bills and going, God damn. So, as much as the affordability angle, there's also obviously the need to cut our collective carbon footprint. Is there anything that we're missing as an issue in the race to electrify as much as possible?
For me, what I look to is the combined system efficiency of the different solutions that are being put forward to us today. So on one hand, if you want to reduce your carbon emissions, we could look to hydrogen, for example. There's lots of talk about green hydrogen and blue hydrogen, all the rest. My personal opinion is that doesn't necessarily make sense in a lot of applications that are ground-based. I think your electric vehicles for cars and whatnot, just because the energy you put in to produce a joule of actual energy at the motor output, the efficiency tends to be quite poor compared to a battery electric. When it comes to electric aircraft, again, the same is true. If you've got a short-range all electric aircraft, the efficiency is very good. You can get drive cycle efficiencies of 90% plus, and if you count the charging as well, it's not much lower than that. When it comes to hydrogen, though, I think that's definitely going to be in the domain of long-range electric aircraft, and that's where it does make a lot of sense, in my opinion. So, yes, I would say when talking about different electrification options, that's the first aspect. The second aspect I think is overlooked is more specifically about electric motors. People tend to write off electric motors as a bit of a solved problem. They've been around for 100 years in constant development. In many ways, they're right. Big, giant electric motors, incredibly efficient devices. And even electric motors like you find in your car are quite efficient. What they don't realize is it's very difficult, even with today's technology, to make an electric motor that's both very efficient and very lightweight. And that's exactly what you need for electric aircraft. In those situations, we really need the best technologies, which is where we're here to help. And also in those situations, even when you've got an electric motor that might be, say, 90% efficient, already very good, if you can take it to 95, although the percentage improvement is relatively small, the auxiliary improvement's incredibly important. So if you think about, say, a megawatt class electric motor that's 90% efficient, you're having to dump 100 kilowatts of energy. If you can take that to 95%, you've only got to dump 50 kilowatts overboard in the case of an aircraft. That makes your radiators, your cooling solution, your drag on the aircraft, everything else simpler and smaller and lighter. And so when people think about electrification, I always encourage them to try and put on their engineering hat and think about the entire system and the way that energy flows through that system and the efficiencies involved. Because unless you look at the big picture, it's very difficult to compare things one to one.
Good answer. Another stock question is, why is it important that Australia have a strong manufacturing ecosystem in your view?
Well, for us, as an early stage aerospace manufacturing company, having a very well-equipped local manufacturing scene is hugely important. We need to move as fast as possible. As a startup, it's really our only advantage over the bigger players. We're definitely not more well-funded than them. We definitely haven't got the decades of experience that they have, but we can move very, very quickly. And so being able to go up the road and have, in the case of where we are here in Notting Hill, in Victoria, in Clayton, we have a dozen different suppliers for CNC parts, for water jet cutting, for laser cutting, for suppliers, for bearings, and every other component you can think of. If we didn't have that, or if that capability was to shrink, we wouldn't be able to move as quickly as we can. And that's when it does become very difficult to compete with some of our international players, especially those in Asia who do have all this stuff on their doorstep. And so for us, it's incredibly important to have that. At the same time, it's also, we've got some of the best engineers in the world here. We've got companies like Bosch and others who do a lot of the design work here. And having that manufacturing capability means that those engineers have places to work, and you're not just producing all these great graduates who are then heading directly overseas. So, there's kind of the two aspects there that we look at.
And so that's everything I wanted to ask, Richard. If there's anything you want to say in closing, perhaps a plug or some final comments, you're welcome to make those now.
Yeah, of course. Look, if anyone's keen to hear more about what we're working on, you can find us at kitemagnetics.com. We're currently looking, of course, always for more potential partners in the aviation space, always recruiting for fantastic young engineers who are looking to work in early stage deep tech hardware startups. So if anyone would like to learn more, please either jump on our website or even reach out to me directly. You can find me through the website or on my LinkedIn page.
Excellent. Well, Richard, it's been a pleasure speaking to you. Thank you very much for joining us here on AU Manufacturing Conversations.
No, my pleasure as well. Thank you. Anytime.